Spectroscopy relies on electromagnetic radiation to probe the structure of molecules and other things. And it's pretty amazing all the things that scientists have discovered. They can learn about the universe using spectroscopy. So let's look at different electromagnetic radiation and how it'll affect molecules. So these aren't numbers you have to memorize. I'm just showing you a lot of this because it's pivotal to science in general, and then we'll focus on NMR at the end. So we're going to look first at these electromagnetic radiation in terms of wavelengths, and I'll order it with, on the left, the shorter wavelengths, and then on the right, the longer wavelengths. So on the short wavelength side, the distance between the peaks or the valleys is the wavelength that can be measured. And let's see what we got here. So first, a very high energy electromagnetic radiation is X-rays, which you could use to make X-rays of your hands and the heart symbol. And so the X-rays have a wavelengths that are super short, as is trying to represent with this graphic here. X-rays their wavelengths are from about 0.1 nanometers to 10 nanometers, so tiny. Remember, a nanometer is 1/1000th of a meter. And next up, we'll look at ultraviolet. Ultraviolet is 100 nanometers to 400 nanometer range. We as humans don't see ultraviolet light, but other animals can, like parrots and butterflies and other things can actually see in the ultraviolet. It's pretty interesting. So for example, this green-winged macaw, when you take a picture of it just looking at its visible light, we have the image here. You can see it has a white beak, a whitish beak, and a whitish face with the black lines. And then when you look at an ultraviolet photo, this isn't really ultraviolet light coming at us, but the instrument is showing us what it's collecting the data of. And then when you put these two together, this is what we suspect the macaw actually sees when it sees other macaws. So for us, the beak looks kind of white and the face around the eye looks white with the red rings. But for them, the beak is more yellow and the white. So they see things different than us. Pretty interesting. If you want to look into this, you can see this website here. And it's interesting, if you go to the pet store, you might see like a white parakeet, but other parakeets might see all kinds of stripes and other patterns in those feathers, not just the white that we see. Interesting. And then next up in wavelength is the visible light that we see. So visible light we see from about 400 nanometers wavelength to about 700 nanometers. So we zoom in on that, you can see I have the X-rays, gamma rays. I left out gamma rays, they're even higher energy than X-rays. And then we have the ultraviolet that the birds and things can see, and the visible, which we can see. And the shorter wavelengths, that's the purples and violets and blues. And the longer wavelengths are the reds over here that we see. And then, so it's interesting. And next up is so the shorter wavelength, you got the blue, violet, and then the longer is the red. So the song I remember teaching Michaela, my daughter, she was younger, is red, orange, yellow, green, blue, and purple too. So you got the different colors, right? And next up we have the infrared electromagnetic radiation. Infrared light, we can't see that or perceive it, but we can use night vision goggles, and you can see it when you wear night vision goggles. Things that are emitting, things that are warm emit infrared light. Infrared radiation. So this mouse is emitting, it's warm, it's emitting in a cold night, so the ground might be cold. And if part of the ground, like this black spot, or anything that's the same color as, not the same color, anything that's the same temperature as the air around it, it shows a black, because it only shows warmer than room temperature and cooler than room temperature. So that's how our night vision goggles can show us what infrared, which our eyes can't see. But other animals can. So like a rattlesnake, it has a nostril and then it has a pit organ here. And this pit organ can perceive infrared light. So it can, I don't know if we'd say it sees in infrared because its eyeball sees visible, but this pit organ can detect infrared. So as far as we know, in the middle of the night, dark of night, a rattlesnake could see a mouse crawling across the desert or wherever. Across the field like that. I don't know if rattlesnakes live I think they live in the desert. I know they live out here in Rockland in the fields. Okay, and then, so moving on, we got microwaves. So microwaves, they're longer wavelengths, 1 millimeter length to 100 millimeters. And we use those to cook our food. And then the longest wavelength is for the radio waves. The radio waves have a wavelength of 1 centimeter all the way out to a kilometer. They have a real broad range for them. So now after we've looked at the wavelength, now let's look at their frequency. So frequency, we're gonna set this up from short wavelength on the left to long on the right again, but because we know that the speed of light c equals the frequency times the wavelength, this means that frequency equals the speed of light, the constant, over the wavelength. So frequency and wavelength are indirectly proportional. So a short wavelength of light is actually a high frequency wavelength. And then the long wavelength corresponds to a low frequency. Hopefully this is all review. This isn't like a major thing of what we're learning, but I figure it's good review for you. Okay, and now let's look at their X-rays again. Our X-rays are between 30 ectahertz and 0.03 ectahertz. So exa, not ecta, sorry, exa. Exa is 10 to the 18, huge, right? So it's a lot of hertz. And then a hertz, remember, is a reciprocal second. And what that's referring to is the wavelength cycles per second. So if you were standing right here and this wave was going past you, if you can count the peaks, say, as they pass you, you'd have to count really fast. You'd have to count 30 times 10 to the 18 peaks would pass you per second if you were standing in that spot. So the X-rays are a very high frequency. And then the ultraviolet light is at a lower frequency. It's 30 petahertz to 0.75 petahertz. So peta is another big one. You don't have to memorize this exa or peta. I looked it up. I was just throwing it out there so you hear it if you ever work with this stuff in the future. So peta is a 10 to the 15 hertz. So high frequency. Visible light, it's 750 terahertz to 429 terahertz. That's what we see in the violets, the 750 terahertz, and the 429 is the red. And a terahertz is a 10 to the 12. So the color violet, if it was a photon of violet was flying past you and you can count the peaks passing you, you'd count 750 times 10 to the 12 of them per second. Infrared light comes in, its frequency is about 429 terahertz, so 10 to the 12 hertz, to 300 gigahertz, and a gigahertz, 10 to the 9, a billion, like you might have a gigabyte storage on your computer. Okay, and then microwaves, they range from about 300 gigahertz to just 3 gigahertz. That's their frequency. And the radio waves are the lowest frequency, longest wavelength, 30 gigahertz to about 0.3 megahertz, which you've heard of megahertz. It's a mega is 10 to the 6 million, so 0.3 million hertz. Now let's look at their energy. So we can relate their wavelength and their frequency to energy. Frequency, we can relate it with a Planck's constant. So if you have to get the energy of a single photon, you just multiply the frequency in hertz to this value, 6.626 times 10 to the negative 34 joules. So Planck was a scientist who kind of was one of the forefathers of quantum mechanics. He found if you have a photon at a frequency of 1 hertz, it's this much energy. All right, so as we saw, I had the higher frequency on the left, lower on the right, and then that means the energy is going to be higher on the left and lower on the right, because energy and frequency are directly proportional. So higher energy, electromagnetic radiation has a higher frequency. And then the wavelength's the one, that's the odd one, it's the indirectly proportional. So the highest energy radiation, electromagnetic radiation, is the shortest wavelength. Okay, here we go. So X-rays come in at about 12 gigajoules per mole. So instead of just looking at one photon of light, we're looking at a mole of photon of X-rays, X-ray photons. So it's 12 gigajoules up to 0.012 gigajoules. Once again, you don't have to memorize this. A giga is 10 to the 9. And then ultraviolet lights, 12,000 kilojoules to about 300 kilojoules. Visible light, 299 kilojoules to 171 kilojoules. So the violet light, the blue, the violets, they're higher in energy than the reds. The reds are lower energy. And you'll notice that most laser pointers are red because they're lower energy, a little safer. And if you get a blue laser pointer, you got to be careful. You don't want to burn yourself. Have it at low intensity. And then infrared light, it's from 171 kilojoules per mole to 0.12 kilojoules per mole. Microwaves lower again, 120 joules per mole to 1.2 joules per mole. And then radio waves lowest energy, 12 joules per mole to 0.2 millijoules per mole. All right, so now the most important thing, though, to consider, the question that led us here, is what happens to molecules when they're exposed to this radiation? Because the molecules can absorb electromagnetic radiation, and we can determine which electromagnetic radiation they absorb, which energies or wavelengths they do not, and we can figure out things about the molecule. So in an X-ray, X-rays, they actually knock core electrons out of atoms. So not just the valence electrons, but the inner core electrons. They can just knock them completely off the atom because they're so high energy. There's a nice article you could check out once my exit thing goes away. That website there, you can go to How Stuff Works. They have a nice thing about how an X-ray machine generates the X-rays. It's pretty interesting. And then ultraviolet light, when it hits an atom, it knocks outer electrons, not the core electrons like an X-ray, the outer valence, but it doesn't knock them off of the atom. It just promotes them to higher energy orbitals, and then they can relax down to their ground state again. And they usually they have to emit energy a lot of times, the ultraviolet or whatever light they absorbed. And so visible light, same thing. When a visible light wave hits an atom, and it promotes an electron in an orbital to a higher energy orbital, and then that electron can relax back down to the ground state. And infrared light, it does something interesting. It doesn't mess with the electrons in that it doesn't promote them to higher energy orbitals, or like the high energy X-rays that knock them off of the atom. They make the covalent bonds bend and stretch. It's like disco. So yeah, I'll show you animation of this. So imagine we have a carbon with two hydrogen atoms bonded to it covalently and some other atoms. When the correct infrared radiation hits this, it causes it to stretch like that. It looks like a cheerleader kind of. This is a symmetric stretch because each hydrogens are stretching out at the same time. And if a slightly different energy of infrared light hits that molecule, it can cause the hydrogens to stretch like this in an asymmetric manner. It looks like cheerleaders are. Makes me think of disco, like boom, 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 ba-dum, 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 boom. See how they're dancing. And they even have, besides disco, we have rocking too. This one's called rocking when they're not so much bend. It's more of a bend than a stretch of the bonds. And that one's rocking. So different energies of infrared light will cause this stretch. A different energy will cause this. Different energy cause that. And if you can tell which energies of infrared light are being absorbed by a molecule, it tells you about the structure. And then next up, we got the microwaves. So you've seen microwaves. You've probably used them lots, right? And what they do is they make the water molecules rotate back and forth, which causes friction and then heats your food. So microwaves oscillate the microwaves within the microwave oven. So when you're oscillating those microwaves within the oven, it makes the water molecules want to try to align with it because the water's polar. So it'll try to align one way, but then the microwave in the oven switches, so it turns back that way, and it keeps turning back and forth, kind of like I made this GIF. And I don't really love this one because I think it should be more of a twisting of the whole molecule, but that's okay. It's basically the water molecules are vibrating, and that causes friction. It heats your food. And that's why like an ice cube doesn't melt very fast in a microwave, because it's in a crystal structure where it can't vibrate. So ice cubes don't heat up that much, don't melt that much faster in a microwave because they have to, the outer water molecules melt on the outside of the ice. They have to heat up, but the inner crystalline ice doesn't heat up. All right, and then lastly, we have radio waves. So what do radio waves do to atoms? Radio waves can excite atomic nuclei which have spin to higher energy spin states, which when in a magnetic field, this is NMR. So NMR uses radio waves. We figured it out finally. So in an NMR, we don't use microwave, infrared, visible. We use radio waves. So back to our animation I showed you before, NMR excitation. So remember, nuclei like hydrogens can have spin into them, and that spin, when it's not in a magnetic field, there are two spin states, alpha and beta. They're the same energy. You put them in an NMR with a very strong magnetic field, and the spins get separated in energy. The alpha spin state, which is in a line, they're both pointing up with the NMR's strong magnet, it's lower energy. And then the hydrogen atoms that happen to be opposing the magnetic field, it causes these to be higher in energy. And then we hit this with electromagnetic radiation, and we can excite an alpha to a beta, and we have a detector that can say, oh, we had a photon of electromagnetic radiation corresponding to this energy was absorbed, and that tells us about the structure of the molecule. And what kind of energy is this? What kind of electromagnetic radiation? Radio waves, that's what we just finally worked up to. So it's radio waves that cause NMR excitations and give us our spectra. I heard when I was an undergrad, my physical chemistry teacher said he had a friend who was working with tungsten NMR. So tungsten's the metal in like old school light bulb filaments. And his experiment wasn't working. He couldn't figure it out. And it was because there was a country music station in the area that was interfering with their radio waves, or interfering with his experiment. But he just had to adjust the magnetic field of his instrument to get it out of that country music station wavelength. And once he did that, he got his NMR experiment to work. He got his dog back and his wife back and his job back. Just kidding. All right, so a detector keeps track of the energy, the frequency of the light that is absorbed, and it makes a spectrum from this.